Hello everyone, I'm Dr. Laura Caggiu from the University of Sassari. Welcome to this module on the eco-friendly route in solid-state chemistry, where we'll explore sustainable synthesis strategy on the advanced material. This approach follows the principle of the green chemistry, reducing energy consumption, minimizing waste, avoiding solvent, and are fully aligned with the goal of the circular economy. Traditional solid-state reaction require the reagent to be in close contact, principally achieved at very high temperature. This led to a large energy consumption, sometimes undesired products. To overcome this issue, two sustainable solid-state routes have emerged: ball mill and microwave-assisted synthesis. Ball milling stands out for its scalability and reproducibility, while microwave heating offers ultra-high energy efficiency and very fast reaction. About ball milling, also called mechanochemical reaction, is defined by UPAC as a chemical reaction induced by the direct absorption of mechanical energy. This process relies on collision between the balls and the powder inside a vial and can be tuned through several parameters: type of mill, rotation speed, ball to powder ratio, and milling time. Different types of mill operate with different motion patterns and energy transfer mechanism. The planetary mill with a two-dimensional is ideal for mixing and reduced particle size. The atritol mill has a large number of small bores and high friction, leading to intense particle refinement, and the specs mill generate high energy impact with three-dimensional motion, suitable for alloy and metastable phases. It is also important to choose the right vials for the synthesis because it could evaluate the nature of the powder concerning the mechanical property and the risk of contamination. The rotation speed determines the impact energy transferred during collision. In this paper, using a specs mill, synthesis carried out at different rotation speeds show that these parameters control the reaction time. In some cases, such as at 555 rpm, the reaction does not occur because the impact energy transferred to the powder is insufficient to activate it. In this work, the effect of the rotation speed in a planetary mill was investigated. It was observed that at 320 rpm, ball motion is limited and non-random, while balls confined to the specific area of the vial. At 600 rpm, the trajectory becomes more evenly distributed, resulting in optional milling efficiency. Conversely, at 800 rpm, excessive centrifugal force caused the ball to adhere to the vial walls, decreasing the frequency of effective collision. The ball-to-powder weight ratio is another parameter that defines how much mechanical energy is delivered to the material. The size and the mass of the balls have a strong influence on the efficiency of the milling process. Larger balls generate more energetic impact but fewer collisions, resulting in coarser particles. In contrast, small balls create a more frequent impact, producing thinner and more homogeneous powders. At the same time, the ball weight affects the energy transferred to the powder. In some cases, reactions occur only when heavier balls are used, in order to the impact energy exceed the activation threshold required for the reaction. Finally, if the total ball mass is distributed among the many small balls, the number of the contact points increases, enhancing milling efficiency. The milling time is another key parameter in the ball milling process. It impacts on the reaction time, but it also influences the particle size. Longer milling generally led to the thinner powder due to the repeated fracturing. In summary, ball milling is an economic, scalable and tunable method used for powder mixing, size reduction and synthesis of the complex or metastable material. Let's now move to the second sustainable approach, the solid-state microwave reaction. Microwave-assisted synthesis allow faster, cleaner and more energy efficiency reaction than conventional heating. Why this difference? In the conventional oven, the heating is transferred by the convection, while in the microwave, the heating is a consequence of the interaction wave meter. The key to this process lies in the interaction between the electromagnetic fields and the materials, described by two properties, the dielectric constant and the electric loss factor. Materials with high loss factor heat quickly because they absorb microwave energy very efficiently, as opposed to the material with a loss factor that heat slowly. Another important factor is the penetration dip, that say how much the microwave energy can penetrate the material. If the sample is too large, heating becomes non-uniform, creating temperature gradient with the material. This non-homogeneous heating can affect reaction control and product quality, as illustrated in this image. To ensure homogeneous heating, susceptors are introduced into the system. These materials efficiently absorb microwave energy and then transfer the resulting heating to the sample through the conduction. Carbon is the most used susceptor in solid-state synthesis because of its excellent microwave absorption properties. In contrast, insulators, also listed in the table, are materials that remain microwave transparent, meaning that they have a low level of radiation absorption. As shown in this graph, the presence of a susceptor greatly improves heating efficiency. With a susceptor, heating is fast and uniform. Without it, heating is slow and inefficient. In a complete solid-state microwave setup, each component plays a distinct role. The susceptor surrounds the sample, transferring heating efficiency, and the insulating material prevent heat loss and protect the microwave cavity. Together, they ensure uniform and controlled heating, maximize energy efficiency, and the process reproducibility. And so, what happens if we combine these two types of synthesis method? When ball milling and microwave assisted synthesis are used together, they form a powerful hybrid strategy for solid-state chemistry. Ball milling produces thin, mixed and homogeneous powder with reduced particle size, creating ideal conditions for the reaction. Microwave heating then provides a rapid and energy efficient activation, allowing the reaction to complete much faster compared with conventional heating. Together, these two techniques offer high, sustainable and reproducible approach for the synthesis for advanced materials. In this comparison between microwave-assisted synthesis and sol gel, we can see that both methods led to the formation of pure phase, but with very different energy consumption and reaction time. While the sol gel method offers excellent control over stoichiometry and homogeneity, microwave synthesis achieves similar results in a fraction of the time, with significantly less energy consumption and without using solvent. The chart clearly highlights the advance of combining ball milling and microwave synthesis. In the hybrid route, reaction time decreases dramatically, energy consumption drops, and the reproducibility increases. This synergy represents a green and high-performance alternative to the traditional solid-state route. In conclusion, both ball milling and microwave-assisted synthesis are eco-friendly, solvent-free alternatives to conventional methods. They significantly reduce energy use, waste generation, and process time, while maintaining excellent control over material properties. Their combination of ball milling and microwave, maximize yield, scalability, and energy efficiency, aligning perfectly with the principle of the circular economy. Together, they show how solid-state chemistry can evolve toward a more sustainable future. And now, thank you for following this module.